Hello, this is a lesson on the transformation of trig graphs or trig functions. And I'm going to concentrate on the sinusoidal waves. However, the same rules basically will apply with all the other trig graphs, and we will branch off into those more later. But the big concept with the trig functions is that if you are going to start with an original, say, sinusoidal curve, I've got sine theta going here, but any other trig function, that the regular rules for transformations that we learned about earlier still apply. So if you look at the general expanded form, f at theta, I'm using function notation, but I could just call that y, is equal to a sine bracket b theta minus c bracket bracket plus d, where theta is the x variable. And the transformations behave very much the same as what we did earlier, as I said. There's a few things that are specific to trig that in terms of of the terminology, but otherwise things are identical. So as before, the parameters a, b, c, and d stretch, reflect, and translate the original function. And one thing is, out of convention, we use that variable c to represent the horizontal translation, whereas sometimes in previous lessons the letter h was used, but it really refers to the same thing. So let's make a few observations. First off, with the vertical stretches about the x-axis, and I'm calling it the x-axis. It can also call it the theta axis because in either case it's going to be the horizontal axis and a vertical motion. So let's start off by comparing a couple of curves. y1 is equal to cos theta, y2 is equal to 2 cos theta. So on your calculator, I'm not showing this, but you can enter them both as cos x, and then y2 would be 2 cos x. And you should get graphs that look somewhat like this. And not surprisingly, we do have the red graph has been vertically stretched about the x-axis by a factor of 2. Now that's exactly what we would have expected. Notice the x-intercepts are unchanged, no difference there whatsoever. But the y-intercept has been multiplied by 2, and in fact every y-coordinate along the way has been multiplied by 2. So we would say this is a vertical stretch by a factor of 2 about the theta axis or the x-axis. Now that's correct to write it like that, or to describe it like that, but most of the time in trigonometry we would simply say that the amplitude is 2, the height of the wave from the center to the very top, the crest. Now let's compare a couple other ones. First off, y1 is equal to sine theta. y2 is equal to sine theta over 3. Now if you're going to enter this into your calculator as is, you have to make sure you do close that bracket around the x to avoid any confusion. However, to analyze that function, make sure that you recognize that dividing by 3 is the same as multiplying by a factor of 1/3. So in terms of the amplitude of the vertical stretch factor, in fact, we'd be dealing with a stretch factor of 1/3. Now I brought up the new curve, or the two curves, so we could look at them. But this is what we would get, and I hope this also does not surprise anybody. The second curve, sine theta over 3, or 1/3 sine theta, will have an amplitude of 1/3. So it has a vertical stretch or compression by a factor of 1/3 about the x-axis. The x-intercepts again do not change. Only the y-coordinates are affected by that stretch. So here I just note what we had earlier. And so it goes. You can expect many variations of these, but the rules still apply. So in fact, this actually helps your understanding of transformations, that is Unit 1 topics. So amplitude 1/3. Now, let's generalize this. If we're talking about any function, sine x, or any sinusoidal function, could be cos as well, y is equal to a sine x will have the amplitude of absolute value of a. Now the reason I put the absolute value around that is because the amplitude is always a positive measure from the center to the top. So if you had a negative a, negative 3, or negative 5, or anything like that, we'd have to be aware that it is going to be a positive amplitude. Let's take a look at some horizontal stretches about the y-axis. These two behave exactly the same way. as previous functions do. This can be tricky though, because there is some of the terminology and the way we approach it is a little bit different, and my experience with the horizontal or with any of the graphing with Trig, it's the period issues that cause the most trouble. So you really want to bear down on these. So let's take a look at a couple functions. y1 is equal to sine theta, and y2 is equal to sine 2 theta. Now we've made a substitution of theta with 2 theta. So from what we know before, we are getting a horizontal stretch by the reciprocal of that factor 2. So times 1/2 about the y-axis. So that's completely consistent with unit 1. So if we take a look at the two graphs first separately, here's our regular sine theta curve. Notice the x and y, the y-intercept is at the origin. It peaks at pi over 2, and one full cycle would be 2 pi. And then, if we take a look at the second graph superimposed on it, sine 2 theta, you can see that it actually cycles every pi rads. So within that regular, that 2 pi of the original, it actually has 2 cycles, which makes sense because it's been stretched horizontally by 1/2. It's been compressed. It's been pushed towards the y-axis. Now here it is on its own, and follow the pattern. You can see that the period is shorter by a factor of 1/2. And the period is pi, as I indicated, and the period is always from one point on a cycle to the same point on the next cycle. That is how long it takes for the wave to go. And if you start at the origin, in this case where I've got the first blue dot, you'll see at pi it starts, there we are again, exact same position. So horizontal stretch by a factor of 1/2 about the y-axis, okay. But we would then also note that the period is pi rads, or if you were in degrees, you could say 180 degrees. Should make sense. We took that 2 pi and we multiplied it by 1/2, or we took 360 degrees and multiplied it by 1/2. So in general, for these sinusoidal functions, sine x and cos x, or theta, y equals sine bx will have, and this is very important, a period of 2 pi over b. Now keep in mind all you're doing is taking 2 pi and multiplying by 1 over b, but this is a nice compact way to look at it. So I would really encourage you to get comfortable with this. Now, if you wanted to do it in degrees, which occasionally you will, the period would be equal to 360 degrees divided by b. So it will be indicated which you use, degrees or rads, but the majority will be in radian measure. And as I said, this is very important to get this down. It's nothing new, but it's a slightly different way of approaching it, a little more direct. So with tan x, now you don't get as many of these. This is not a sinusoidal wave, but you need to remember that tan, if you think back to the earlier lesson, tan has a period of pi rads normally, or 180 degrees. So when we have a factor of b in front of it like this, the new period is going to be not 2 pi divided by b, but pi divided by b, or 180 degrees divided by b, simply because we start with the original period and we multiply by the reciprocal of that b value. Let's do a couple examples. Here we want to get the amplitude and period of each of the following, and then indicate any other transformations. Start off with y is equal to 4/5 sine 5 theta. So lots going on with this one. And that 4/5 in front, the vertical stretch factor, produces the amplitude of 4 over 5. Then we need to find the period. And let's do this one in rads. And we have a b value of 5, and the period is always 2 pi divided by b. So therefore, the period would be simply 2 pi divided by 5. Now if you had converted that to degrees, which is permissible, and then convert back, that would turn into 72 degrees. Now, I wasn't asking you to graph these ones, but I can't help myself. So let's take a look at them. On your calculator, if you're in rad mode, all you'd have to do is enter 4 divided by 5 sine 5x. Now, some people put a bracket around the 4 divided by 5 because they're more comfortable with that, expressing it as, as 1. This looks like the sine 5x might go with the 5, but in fact your calculator knows what to do with it, and you do not need a bracket around that coefficient, that factor in front. But if you put one up, no harm will come to you. And this is what you get for a graph. So because of this fairly severe horizontal stretch factor, compression, this one is cycling very rapidly. If you take a look at the 2 pi, which is the end of the curve, you're getting 5 cycles within that 2 pi. So it's really been compressed quite severely. The amplitude is up at 4/5, so it's a little bit short for a graph too. And there is the period. You don't have good scale measures on this graph. That's certainly usually the case with radian measure ones, but that would be 2 pi over 5, one cycle. And the amplitude 4/5 right there. Here's another one. Negative y over 4 is equal to cos 1/2 theta. And if you're going to graph this on your calculator, or if you're going to make your observations, most people prefer to isolate the y. So you do so by multiplying by negative 4. So y is equal to negative 4 cos 1/2 theta. So let's make our descriptions of this, and then I will once again graph it. The negative in front indicates a reflection in the x-axis, just like it did back before. And then the amplitude is 4. That is a vertical stretch by a factor of 4 about the x-axis. So this will be a fairly tall graph. The period is always found by going 2 pi over b. Now, because we have a factor of 1/2, you probably are thinking already, okay, that's a horizontal stretch by a factor of 2. And you're correct. And that's all you really need with it. But if you use this little formula that's given to you, you simply put 2 pi divided by the b value of 1/2. And then by dividing this one out, remember, you're dividing by 1/2, therefore you're multiplying by 2 over 1. So 2 pi times 2 over 1 will give you a period of 4 pi. So this one has been horizontally stretched, or even expanded, if you like, by a factor of 2 about the y-axis. And it will look like this on your graph. You enter it negative 4 cos, open up a bracket, and what I did was I went 1 divided by 2x, and my calculator understood that that was a factor of 1/2. It is possible to go 0.5x, open up a bracket around the 1 divided by 2, and then so you keep it together. That will also work. But this is sort of the cleanest way to enter it. And then your graph matches what we expect to get. We have an amplitude of 4, so it's a much steeper curve. Notice that this one has been reflected around the x-axis. Now I'm going to draw more attention to this in future lessons, but instead of having a y-intercept of 4, we have a y-intercept of negative 4. So the graph has been flipped over. And if you take a look at this horizontally, you'll see that the one cycle, if you went from trough to trough, that is the low end of the curve to the low end on the curve, you can go anywhere, but that's the most convenient spot, I think, you will see that the period is 4 pi. So from that point to that point, 4 pi instead of the regular 2 pi. So you really have to watch careful with what you're doing with these. It's a lot of analysis of graphs because trig functions aren't as easy to inspect as are other curves that we worked with in Unit 1. You really have to watch quite carefully with them. So that's it for me.